Let's now go ahead and adapt our model such that we use the BERT model for transfer learning. Instead of having this first part here, which takes in the context, that is, we have the encoder block and then this other encoder block, we are going to replace all that with a BERT model. Specifically, we are going to use the distilled BERT model, which is a variant of the BERT model, but it's more lightweight as it contains less number of parameters. Also, coming from the fact that the BERT model is designed such that both the context and the question could be passed directly as inputs, we don't need to specify or define two separate models to take in the context and the question as previously we had seen. So here we simply have to define our model such that, or define our data such that we have as input firstly the CLS token, followed by the context itself, followed by the separation token, followed by the question itself, followed by a separation token, and then followed by some padding tokens. And also the padding is done such that the sequence length is 256. So if we have a sentence less than 256, we just add the padding, or we just add a certain number of padding tokens such that we have the sequence length being equals to 256. Now once we get this, we are using a distilled BERT model whose model size is 768. So what we get as output here would be a tensor of shape by size by 256 from the sequence length by 768. Now note that this is very similar to what we had seen with the word to vec. That is, we're taking an input of very large vocab size, or say vocab size of 30,000, 300,000, 3 million, and then at the end we have this outputs or embeddings of dimension 768. So we're going from whatsoever vocab size to 768. Now once we get this, given that our encoder blocks right here may not always have the same model size as with the distilled BERT model, we could include a dense layer such that the number of output neurons of this dense layer is equal to the model size of the encoder blocks right here. In the case where we want to maintain this model size, we will not need this dense layer. That said, this distilled BERT model could be used to do transfer learning. In the first way, the parameters of the distilled BERT model aren't trainable. So once we pass in an input, this just helps us extract rich features from this input, which is represented by this output tensor right here. In the second way, we could allow this model's parameters to be trainable, and so we'll be fine-tuning this model. In this practical section, we shall be freezing this model's parameters, so they'll be untrainable. We'll just use this model to extract this rich features from this inputs, and that's what we pass into this encoder blocks. We do the same concatenations, then we pass through a dense layer with softmax activation. Another simplified way of approaching this problem is by making use of the way the BERT model takes in data. Recall that if we have this first portion as a context, the next as a question, and the next as a pattern, then for every input we know the context length, we also know the question length, and we know the pattern length. We know that the context length plus the question length plus the pattern length, including the seps, that's the separations, and the CLS, would total to 256, which is the sequence length. So all this is the sequence length. Now if we have this context length, then once we get the output, we take only the first C parts of the output. So instead of taking the whole, that's the whole sequence length, that's the 256 by 768, we're going to take C by 768, which is just part of the whole sequence. So we take in those first C sequences, or the outputs of the first C sequences. Then once we get this, we pass this output to a dense layer which has only one output neuron, such that we have this new tensor of shape byte size by context length by 1. Then we reshape it to give us byte size by context length, and then we obtain this kind of output from this, wherein all the values are zeros except where we have the start and the end positions. And this now can be trained end to end, such that we have an input, we restrain the output, and then we train this full model such that based on the context and the question, we are able to select portions of the context which give the answer to the question. And that's exactly why in the paper you see here that after pre-training on the BERT, that's after this initial pre-training step, the BERT now could be used in this squared data set, as you can see here. In the paper, the question actually comes before the context, because here's the context, here's the question. So here again you see the cut out this part, that's they don't consider this first portions, and then it's only the work with this last with a section which contains the paragraph, wherein the loss is computed based on the outputs. The pre-trained model we shall be using will be from Hugging Face transformers. So right here we see different models, the BERT, then we get to see the distilled BERT. This is exactly what we're going to be using, and we have a host of other transformer based models. Here we have this list of model, and then the TensorFlow support. So we can see there's the support for Albert, BART, BERT. Then the distilled BERT is supported. There's a TensorFlow support for the distilled BERT. And also, given the fact that Hugging Faces continues to better the services, most likely in the nearest future we will have full support for TensorFlow. So that said, we get to the distilled BERT right here. Click on that, and there we go. We have this distilled BERT documentation. Then again we could specify that's the TF distilled BERT model right here. So with this we could select that TF, that's the distilled BERT for TensorFlow. And here we have a very detailed documentation of how to use the distilled BERT model with TensorFlow. To install this Hugging Faces transformers, you just do a pip install transformers. So that's it. Then here is a simple example of how this is used. As you can see here, this is from the documentation. We have from transformers, we import the distilled BERT tokenizer and then the distilled BERT model. But in this case, we specified as a TensorFlow model, so it could be used seamlessly in TensorFlow. Now we have we've done this already, so that's it. Let's take this from here, and then we include it right here. That's it. Run this. We first of all start by defining the tokenizer. So here we have the distilled BERT tokenizer from pre-trained, and we'll specify the distilled BERT base uncased. Then for the model, we have the TensorFlow distilled BERT model, which we've imported already. We specify distilled BERT base uncased. The role of this tokenizer right here is to convert this words or this input sentence into a tokenized form, in which these words have their corresponding values in a BERT vocabulary. So with this, we could run this and ensure that you have a internet connection, so you could download this model in the case where you've not had it. And since we've downloaded already, we just have this warning right here. Now once we get this, let's print out the tokenizer. So print that. This shows us that the BERT model, which we're working with, has a vocab size of 30,522 words. The model max length is 512. Is fast is set to false. The padding side is the right, so you're not expected to do padding before putting in the sentence. You have the sentence before the padding. Then we have some special tokens: the unknown token, the token, that's the separation token, the pad token, the CLS token, the mask token. Now let's consider an input, say tokenizer of, let's take the same input right here. Let's have this first part. So we have this here, put that out, run it. There we go. So this is what we get after doing this. From this, you see we have hello, my dog is cute and I love it so much. So notice that here we actually have hello, comma, that's one. That's, it says this comma is part of the vocabulary. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we'll not consider this first. So let's take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now this 101 corresponds to the CLS. So if we add a CLS, you'll see we would have a double 101. So let's run this again. See, we have double 101. What happens here is this tokenizer automatically includes a CLS without you having to do that manually. So we could take this off and you see we have just one. So that's a CLS. And then the separation, like you can see here, is 102. So CLS is 101, separation is 102, and all this you could get in the documentation which we have just. And then the padding is a 0. So let's do this here. Let's say we have the separation, run again. You see, you notice that we have 202s. Then if after the separation we have a padding, that's padding. Okay, so you see that you have the separation, you have the padding, so we have the 0, and then we also have the separation which is added on automatically. Then if you have this kind of input where like you have this, let's add this here. So let's take this off. That's fine. We have that. So let's run this now. As you could see right here, we go from 101, and then we have the separation right here. The separation comes from this, so it automatically sees that this is the first part or the first input, and then there needs to be a separation. So once you do this, you're just like putting in a separation. So once there's this, we have a separation, or once you stop with this first string and then go on to the next string, there's automatically the separation. Then we start with this other one, and then we also have this automatic separation at the end. So instead of doing this, you could see here we could count also 1, 2, 3, 4. So you have 1, 2, 3, 4. Now instead of doing this, we could just join this up and then have a separation right here. So if you want to have a separation there, you could just do this, and you see you have exactly the same output. Then since Hugging Face can be used in other machine learning libraries like PyTorch and JAX, you have to specify that you're working in TensorFlow. So yeah, you just have to return this TensorFlow. So the return tensors is actually a TensorFlow tensor. So that's it. As you could see here now, instead of what we had previously, now we actually have a TensorFlow tensor. Then from this, you could specify we want the input IDs, because we're not going to be using the masks. So we want the input IDs, run that, and there we go. We've just seen how this tokenizer works. Now let's look at the model itself. So like with this, you could see here that the model takes in this output from the tokenizer, which is giving you as inputs, and then from this let's print out the outputs, and here's the result we obtain. As we could see, we have this output of shape 1 by 19 by 768. Also, just like with TensorFlow, if we want to render this model weights untrainable, we just do model.trainable equals false. Now that we understand how to use the BERT model from the Hugging Face library, we could go ahead to prepare our data set. A problem we may face is that the way the BERT does tokenization is not exactly the same way we've been doing it throughout this course. So as we could see here, it considers this comma, which is punctuation, as a token. Now supposing that we want to find, or we've defined a position of, or the start position to be where we have this my, that's 0, 1, 2. If we don't have the comma, we'll just have 0, 1, and then the dog to be the second position. So if we're going by the way we've been working so far, we'll not have this, so we'll just have 0, 1, 2. In that case, our start will be 1 and our end will be 2, which is quite different from what we're gonna get if we're working with the BERT model, which in this case is normally supposed to be 0, 1, 2. So if we work with the BERT model, we should have instead 2, 3 as start and end, because here's where we get the answer to our question, what do you love? That said, the way we're gonna build our data set is such that we shall generate this tokenized output right here. Then it is based on the exact positions of the answers in the tokenized output that we are gonna generate the start and end positions. So this means that in this case where we have this is CLS, hello, comma, my, and dog, our start will be 0, 1, 2, 3, and our end will be 4. Doing this will make us ensure that we don't make errors in locating the start and end positions. And that said, we'll create this kind of data set. Now let's look carefully how this data set is created. As you can see here, we start with the CLS. So let's take this here. Let's do this. This is one data point actually. Here we start with the CLS. We have the context, so a long context, and then we'll get a certain point. That's this. We see we have the separation. Then we go with a question. After the question, we have the separation. Then we have the pattern to the end. Now, based on this tokenized output right here, we are going to locate the start and then the end position. So we don't locate the start and end position based on the input sentences. We instead do that based on this tokenized outputs. We shall also see shortly that putting our data set in this form will make it easy for us to work with the TensorFlow data sets. Then to create the data set we just saw, it's similar to what we had done previously. We'll still again get to the squat.json file. We have the squat hugging.txt file which we want to fill in with our data set or with a different data points. We have this in talk, that's the input which has been tokenized. We see here we have the tokenizer which takes in the context. So first we have this tokenizer here which takes in the context. Then we include the separation. After the separation, we take in the question. Once we take in the question, we return the tensors as TensorFlow. We select the input IDs and then we take this as a numpy array so we can easily do modifications on that. Then after getting that as numpy, we take this also as a list, so it becomes easy to work with this input tokenized or this tokenized input. Now we need to add the extra tokens, which are the patterns. So basically we have the sequence length, which we've defined already here, minus the length of this input. Then we adding up the required number of pattern tokens. Once we have this right, we take this input and then add it up with the extra tokens, that's the padding tokens. And once we have that, we go ahead to get the position of the start and the end. As you can see here, what we're passing in is the tokens, and then we're specifying that we're getting the numpy array. So what we pass into this get position function, which we've defined previously, is actually the tokenized context and the tokenized answer, such that the positions are gotten with respect to the tokenized outputs instead of with respect to the input words. Once we have this fine, we just repeat the same process we have been doing previously. That is of writing in the token, then we write in the initial and the final positions. To test this, let's take this off. Let's just do it for 1. So here we have 1. Take this off. Here we have 1. Then let's also print this. Let's print out some values. So we shall print out the in talk. We shall print out the in talk right here. Then we shall also print out the tokenized, that's this values we get from here. So we shall print out this here. Take this, put it out here. Then take this too. Put it out here. Let's print that out. That's fine. Now let's print out also the initial and the final value. So print out initial and the final. Okay, so we could run this, and yes, what we obtain is output. We could see clearly from here we have the input, which is this. Then we have the input with the patterns. That's it. Let's take this from here. Input with the patterns. Then once we get the input with the patterns, we're supposed to get 2 of this. Let's go back to this. Let's print this out. Take that. Then we should have this. Print that out. So we take this. Okay. So we take that off. No, this is okay. It's instead this here. So we cover that. Okay, so once we have that, let's run this again. There we go. We see we have this. Okay, we have this one here. So we've printed out the input token with padding. Then we have this first input to the get position function, which basically is made of the input token but with the context. So as you could see, if you look from here, we have 101 to 20,773. So that's basically it, up to this point where we have 102. So if you could go from 101, you should have 102 somewhere around this. Yeah, there we go. There's it. So we have 102 here. Before 102, we have 1012. So as you could see here, we have that. So basically, this is the context, and that's what we have in here. So that's the context. This is the context, and then followed by the question. Same with this, but followed by the question and also the pattern. So here we have the context. This first part is the context, and then what we now have is a tokenized answers. So if you look carefully in here, that's in the 67th to 70th positions, you would see this 4 tokens right here. And there we go. Here, there you have 999, 996, 2397, 4134. So there we go. Here are the positions where we have the answers in the context. So what we're going to pass in now into this get position is the context and this answers, and with the get position method we're going to localize the exact position of these answers in the context so we don't make errors. And as we had seen here, this is what our data set looks like. We have the context, we've seen this already, so we basically have the input and then the exact positions. Once we've had our data set prepared and stored in this squat hugging.txt file, As usual, we could define a number of examples, the validation ratio 0.8, rather 0.2, then the validation bridge. Then we have this text data set, which is created from reading each line in the squad hugging.txt file, which we've just seen. We'll define the sequence length and then the batch size. Run this. And this is what we obtain for our text data set. So for each line we have this. Notice that this tensor which is created is a string. And basically this is a string in question. We have the string. And the way the string is built is such that it actually looks like some list. The reason why we did this is because we are gonna, or it's gonna make it easy for us to convert this into an integer, or rather a tensor of type integer, which will be made of this first part as input, and then we'll have this to start and end tokens right here, or rather start and end positions. And so as we could see, we will need to transform this string into this input tensor and into this output. So first thing we do is we split this based on the type string. So based on this, we'll split this into 3 parts. This first part, the second part, and then this third part. So after splitting, we're taking the first part, which is the input. This is basically the first part here. This is the input. We replace this commas, which is actually a punctuation sign, by a space. Once we do that, we now split the text. So what we'll be having will be a string now made of just this, space that, up to this last value here. So we now split this using the strings that split function. And it will convert this now into a tensor, where each of these elements which make up that tensor will be strings. Then the next thing is to convert this tensor of strings into a tensor of numbers. So that's why we have the strings to number right here. And then more specifically, we cast this into an int 32. That done, we now move to the output. For the output, we have this first, or the start, and then we have the end. So for the start, as you can see, we get the start here. We have the start, and then we convert it into its one hot notation. And similar to this, for the end, we take the end, and then we also convert it into its one hot notation. Run this, run that, print out one input or one data point. We have the input. So we see now that this is a tensor of type int, unlike here where we had this string tensor. We see the D type here. So now we have that this is our input, here's our output, this one hot vector where we have a 1 at this position, that's the end, and then for the start a 1 at this position. Then also notice that the sequence length is 256. Once this is okay, we could now shuffle. So here we shuffle our data set, and then we put this data set in the batches, we cache it, and then we use the prefetching to make our training go faster. Now that is done, we get started with the modeling. We've done this already. We're going to use the LSH attention for this task. So we just run all these models right here, run that, and then coming now to this final model which we shall be using, we define this BERT model here, which we saw already. So basically we're defining this BERT model. We render all the weights to be false, so we are not going to be doing fine-tuning. We shall just make use of the already trained weights. And then once we define this BERT model, we have our input. We've defined our input already, so here is it. This is our input, and then we pass this input into the BERT model. Recall that our input is defined such that it has already been tokenized. So with this kind of input, like what we are seeing here, it has already been tokenized, so we don't need to do tokenization before passing into the BERT model. Let's get back to that. We have this in our BERT model. Then the output from here gets into the first encoder. This is now passed into the next encoder, and then to the third encoder. We create the head start by concatenating the first and the third, and then the head end by concatenating the first and the second. We also include softmax, and our model is now created. Could run that. There we go. We have this model with over 105 million parameters, with 66 million coming from the distilled BERT model, and then the rest coming from encoder layers. You should also note that there are even more lightweight variants of the BERT. So the other lightweight variants could be used depending on the kind of task you want to solve or the kind of accuracy you want to get. Although obviously we want to get the highest possible accuracy, but if we want an environment where the resources are limited, obviously we wouldn't be using a model with too many parameters. And also care has to be taken to avoid overfitting a model. So that said, we can now go into training. We had this defined already. Run that, and we run the training. After training for several epochs, as you could see, the loss drops. So we've overfitted on some small part of the data set. So we have this drop in loss. And then we could go ahead and test our model. Now, the way we shall do this testing is by simply, first of all, defining the context. So here we have this context from the part of the data set we trained on. That's this context right here. Then we include this SCP token to separate the context and the question. So here we have the context followed by the question. What was the name of Beyonce's first solo album? And then these two now combined to form the input. Obviously we have the tokenizer, so we simply use the distilled BERT tokenizer from Hugging Face. Here we have this tokenizer defined as we've done, or as we've seen previously from this pre-trained distilled BERT right here. This input is passed into the tokenizer. We specify that the output or the returned tensor should be of type TensorFlow, so it's a TensorFlow tensor. That is now this input token right here. Then we do padding so that we could match up with the kind of inputs our model was trained on. That is an input of size 256 or sequence length of 256. We include an extra batch dimension, and then we pass this into a model. So right here we could print out the output. Run that. There we go. We have these results. We have the output 1, which is this tensor right here. Then we also have the output 2. That is it right here. We have this output 2 tensor of shape 1 by 256, and this 2 1 by 256. To obtain now the start of the answer, we'll simply look for the argmax of the output. That's out1, which is this. And then to obtain the end, we'll go in for the output of out2. That's actually out2, which is this. So here we could do a print out the start, and then we could also print out the end. Run that. There we go. We have 124, 126. Now that we have the start and the end positions, it simply means we could go, or we could get into this input token right here and then locate the word at the 124th position up to, or we locate the words from the 124th position up to the 126th position, so that we could get the answer to this question. And to do that, we could initially define this word right here, this empty string, and then we'll get in this range from start to end. Basically it's this. And since Python goes from, say if we have the range of from 0 to n, Python will go from 0 to n minus 1. So that's why we go to n plus 1, so that we go from start to end. And then with the input token, we shall get the ith value. So basically we're getting the input token, we're getting the ith value. And since we're getting just tokens, we need to actually get the words which correspond to these values. So that's why we have a tokenizer decode, which converts these tokens into actual words. Now to separate these words, we just add this right here so that we could see clearly the answer. So with this, we run that and we have this answer: dangerously in love. So this is the first word at the 124th position, 125, and then 126.